Hello and welcome back to Calculus 3, section 16.2 on double integrals over general regions. Last time we had rectangular regions and our limits for integration for both integrals were all numbers. And they were all numbers because those numbers actually represent the lines that bound our region. So the integral, the double integral from last time, that was, let's say, a to b and then c to d of some function f dy dx, as a domain had these x, y. So had this here as a, but this line is x equals a. Had this value as b, and this line is x equals b. And it had this value here as c on the y-axis, and that makes this line y equals c. And then had this as d, which made this line over here y equals to d. So you see that we are able to actually create this rectangular region by using these 4 linear lines, and each one of these was actually a constant, number, and that's why we had all numbers. So you will always be able to recognize rectangular integral if you see all numbers around. Now in 16.2, so this was 16.1. In 16.2, we are going to have functions to bound our integral. So now my domain, or the region, what we're looking at, might have, let's say, a function and then another function. So you have f of x and g of x, and now you have your region R inside. So your region R is now this. That's region R. It's no longer rectangle. Now these two regions will intersect at points A and B, and I hope it doesn't make too much brain power to just say that the volume in this case will be double integral of f of x, y. This is the wavy surface that goes on top. And let's say you have dy dx over here. Note that your x is still between a and b. Oh, I gotta switch these functions to g and h. Sorry, g and h, because f is already used up. So I'm switching the functions to g and h. So lower limit is going to be h of x, and the upper limit is going to be g of x. You are enclosing the region with the functions and values you have. So for me to bind this region, I need to do it from left and right, from top and from bottom, from all 4 sides. So you're asking yourself, what is the freedom of movement here? Left and right, you can go as far as A and B, and that's x motion, right? Left and right is the x motion, and as far as you can go in this problem is A and B. So limits for x in this case are A and B. And as far as you can go up and down, well, the lowest you can go is g. No, lowest you can go is h, and the highest you can go is g, which is why those are your limits on the inner integral. So now when you integrate out y, you will plug in the functions h and g. Those are in terms of x, and then the next integration kicks in, which is x. It's going to integrate out x and just plug in the numbers, and you have the value. Let's talk about the stencil again. Remember I mentioned the cookie stencil before. You press that into a cookie dough. Whatever stencil you have is the shape of the domain. And that is what you're bounding by the limits in the integral. The top of the cookie, whatever shape you have, is f of xy, which you plug inside the integral. And the rule is the same. If you are figuring out the volume, you will have f of x inside. And if you remove f of xy, what do you get? $1 million question. What do you get if you remove f of xy? If you are considering this, what area? Yes.
Oh.
What area? What area do you get? It's a specific area you learned before.
Area between two curves.
Yes, area between two curves. Do you guys recall your Calc 1 and Calc 2? Wherever you learned the area between two curves, it was top curve minus the bottom curve. The formula that you learned, most of you learned it in Calc 2, was that if you have two functions intersect and the top one is f and the bottom one was g, it was integral f minus g, integral from a to b, right? A to b, f minus g dx. Well, what happens if you integrate 1? You get y that is going to be computed from a to g, h to g. Well, that's when you plug in g, you get g minus h, and you still have the dx integral to work on. It's the same. It collapses to that formula. So if you have f of x, it's calculating volume. If you do not have f of x, it's calculating just calculus 2 area between two curves. But it's just a double integral version of it. So this would be your integral. And calculation for this is the same. You calculate the inner and then you calculate the outer. There's nothing new there. What's new is the concept. Now, some functions, some regions are not composed of functions. They are composed of sideways functions. So you actually have to work sideways, like that. And for this, the volume is double integral. Now you have f of xy here as well. And now you have dx dy. So the outer limits are c and d. And these functions here are capital H of y and capital G of y, because you have to flip them out. So now your region R is sideways. Sometimes you will have to use this formula. It depends on what shape you have. If you have y squared, well, you have to use this side. Now, the largest issue here is the way to set up the integral, and calculating obviously not a problem. Right? If you know how to integrate, you're done. And usually they're basic for integration. The issue that you guys run into is not being clear which way to set up the integral. Should I use dx dy, dy dx? And also, you should write in capital letters. You cannot switch order of integration here, just swapping it. If you can switch order of integration, it's work. It takes steps and effort to actually switch order of integration. So we'll get there, but let's first figure out how to set up basic integrals. So this is the way I process this information, and if you guys have and can figure out anything else, well, then use whatever else you guys figure out. I want to make sure that dx gets to swipe from A to B. So A to B, and that's A to B dx. Those two things together give me my length. And then the height of the rectangle, the top of the rectangle is touching f of x, and the bottom is touching 0, y equals 0. So f of x minus 0, so it's just f of x. So representative rectangle in one shot gave me everything. As it slides, the most it can go left is A. I'm always writing y equals 0 function, which is I draw a representative rectangle dx again. And to find the area, I say, well, this rectangle again has to swipe from A to B. The top is always writing function f, and the bottom is always writing function g, so f minus g dx. So this is the way I always set up the integrals. I take a look at the top of the rectangle, bottom of the rectangle, top minus bottom, and then obviously left and right is the movement. Now in Calculus 3, so now when I draw my representative rectangle, note that I'm putting up the vertical representative rectangle, which is dx. Whichever rectangle you draw, that's your game with the representative rectangle. It's very important. So I have my two integrals. I know I'm going to stick in the function here. And now I'm just going to put d and d. Always use dx. If your problem is like this, look at your dx. It's touching the same function on top and the bottom. That's no bueno. Or dy, or doesn't matter. Yeah, great. And in our case, well, that's a rip on the stream because, actually no, the stream seems like it's going fine. I think that the projector just gave up. Yeah. So I have a dx, and if I draw dx, what I'm looking for is that the top of the representative rectangle is always writing the same function for the entire trip. And the trip is from A to B. And the bottom of that one has to write the same function for the entire trip. So dx works, so I'm going to put x on the outer, and the corresponding limits are A and B. Now, since dx is on the outer, the y has to be on the inner. And now that's going to be top minus the bottom. So top, which is g, goes on top, and the age of x, which is the bottom function, goes on the bottom. Yeah, I just looked at the at the book, and they have them age on top and g on the bottom, whatever. If you understand the concept, it doesn't matter. I wish you learned this as top minus bottom, right minus left, further away minus closer by. That's much better way to learn than to memorize f minus g or age minus g or whatever. Because situations change. And if you memorize the formula one way and you have zero concept, then clearly if anything changes, you are stuck. So let's take a look at the problem. The first order of business is for us to calculate without setting anything up. They just gave us one of these iterated integrals, we just computed. Here, number 19, for instance, looks disgusting enough. 0 to ln 2, e to the y to 2, y over x dx dy. And they just want us to compute this. That's all. Okay, fine. Let's do it. I am integrating in respect to x. So if I'm integrating in respect to x, the y is the constant. So I can copy y. So I am technically integrating 1 over x dx. What is the integral of that? Thank you. And that needs to be computed from e to the y to 2. And I still have dy. So one more time. I am integrating this. Since I'm integrating in respect to x, y is a constant that multiplies the whole thing. So I just copy the constant. And since I copy the constant, the only thing that I have to worry about is the integral of 1 over x dx, which is ln absolute x. So now that I have that, plug in the limits and go further. So what I have now is y, and now I have ln 2 minus ln e to the y. And I still have dy. So this is integral 0 to ln 2 y ln 2 minus y dy, because ln and e cancel, right? So now I will distribute this so I can integrate. Now I'm back in Calc 1. I have ln 2 times y. ln 2 is like a coefficient. This is like 3y. Minus y squared dy. So integral of y, so ln, oh sorry, I'm integrating. So copy ln 2, and the integral of y is y squared over 2, minus integral of this one is y cubed over 3, and all of that needs to be calculated from 0 to ln 2. So it's just messy. You do one at a time. Plug in ln 2 everywhere. So I have ln 2 and then ln 2 squared over 2 minus ln 2 cubed over 3, and then minus big fat 0 because it kills both of the terms. Now look, you have ln 2 times ln 2 squared. That's ln cubed, right? So that's awesome. I have ln 2 cubed over 2 minus ln 2 cubed, I said, over 3. Well, that's 3 ln cubed 2 minus 2 ln cubed 2 over 6 when you do the common denominator. And then 3 apples minus 2 apples is 1 apple. So ln cubed 2 over 6 is the answer. Now, if you want to get the decimals, go ahead. But we generally don't care about decimals. So that's the procedure. Again, we did not set anything up here. I want to talk about very important skill that you need to have when dealing with double and then later triple integrals. For that, we are going to start with this vanilla problem here before we start setting things up. So 0 to 2, x squared to 2x, xy dy dx. You can integrate this in 2 minutes, it's not a big deal. What I am concerned with in this problem, guys, is a very important skill of back engineering the region. Because the region is encoded in those limits. If you want to switch order of integration, you have to be able to draw the region looking at the limits. So, when I look at these limits, I see two functions. Graph them. There is a function y equal x squared. There is a function y equal 2x. That should be a joke for you to graph. So, we draw the xy plane, and then the easy one to graph obviously is the linear line, the slope 2, and then we have the parabola. Now it's good to draw as precise. I mean, I can go like this, but no. X squared goes through what points? It goes through 0, 0, goes through 1, 1, and then symmetric, goes through 2, 4, and then symmetric. It goes to 3, 9, but we don't care because they already intersected there. So I'm going to draw in this. So I hope you guys see now, and I'm going to also tell you that there is a 0 to 2 on the outer integral, right? Now look, when I zoom in here, this region is the domain of the integral. If you draw representative dx, do you see that the top is always riding 2x function? The bottom is always riding x squared function. It goes left, all the way left to 0 and all the way right to 2. So it's bounded from all four sides. And those are exactly the limits we had. So it's not just, oh, I give you the region, you can write the integral. Also, if I give you the integral, you should be able to draw the region, because the method goes both ways. So now we can go and we can, integrate and do all of that stuff. But at least we know what the region is. The way I did this again is I looked at the functions given to me, I graphed those functions, and then you cut with your 0 and 2 to make sure that it's in that. So now to integrate this real quick, we have 0 to 2, integrating in respect to y, so it's xy squared over 2, computed from x squared. I have 2x squared minus x squared squared dx. And I just need to clear up this annoying algebra. So 0 to 2, x over 2, 4x squared minus x to the 4th dx. So the now last step, integral 0 to 2, you distribute, you can kick 1/2 outside, and you distribute x, 4x cubed minus x to the 5 dx. And we can finally integrate. So copy 1/2. Integral is x to the 4 over 4. that kills that. So it's just x to the 4th minus x to the 6 over 6, computed from 0 to 2. So 1/2, open parenthesis, 2 to the 4th is 16, minus 64 over 6. Well, one of the 2's will cancel. So 32 over 3. And it's equal a number. You can go and calculate if you know. It's 8. Well, we can calculate quickly because you can actually hit it with a half. When you hit it with a half, you get 8 minus 16 over 3. 8 times 3 is 24 minus 16 over 3. And that's 8 over 8/3. What is this 8 over 3? It's the volume of the object that it's on top of that, what we have. To find the volume of this doorstop, hold on, yeah. Do I use 16.1 or 16.2? To find the volume, yeah. 16.1, right? Well, don't let's use the basic geometries, the triangle, right, times the height, you get done, right? But yeah, see, this is a rectangle. Sits on it. It's a rectangle, so rectangular region, and then you have the plane. So you have to figure out what the plane, project question, right? You have these basic shapes when you want to learn your engineering drafting, right? In AutoCAD, they give you first stuff like this. They're all great also for Calc3 integration, because all those shapes in the beginning are basic, right? So you can do these kind of things. Another problem that I'm just going to outline, we're not going to solve this because you'll see why. We are going to deal with this problem in much better light. I have negative square root of 16 minus x squared, positive square root of 16 minus x squared. I have 2xy to integrate, and then dx. Oh, well, it should be dx dy. I'm going to change it to y dy dx, so because I messed it up. Anyway, what do I have here? What am I integrating? I'm integrating some shape that it's over a circle. So the stencil is the circle. The function here is y equals negative square root of 16 minus x squared. Well, square both sides, it will kill the minus. You get y squared is equal to 16 minus x squared. Move the x squared on the other side, you get x squared plus y squared equals to 16. That's a circle of radius 4, right? So now, if I draw my circle of radius 4, the top portion here is square root of 16 minus x squared. The bottom portion over here is negative square root of 16 minus x squared. That's what they are. And you see that my dx is trapped inside the top, always riding the upper square root, which is the upper limit, and the bottom of this dx always riding the orange, which is the negative square root, also given in my integral, right? Am I integrating the whole circle? Look at it. It doesn't say on my forehead. Look at the picture. Am I integrating the whole circle? Look at the integral. Yes or no? It's clear. Am I integrating the entire circle over the entire circle? Why not?
Only integrating the right half.
Exactly. I am only integrating right half because it's from 0 to 4. 0 to 4 is only the right half of the circle. If you want the full circle, then you have to go from negative 4 to 4. All right, so meditate on that a little bit before you go. Guys, this skill is far more important than your ability to compute the stupid integral. You have technology to integrate. The computer cannot set up these things for engineering. You want to be a mechanical engineer, you want to figure out the volume of the part that you're working on, you have to know these things. Setting up integrals is important. You let the computer integrate, right? If I didn't have to, bother you with process of integration, trust me, I would not waste your time. Because the computer can do it in a split second. The most important skill for you to have so you can actually be a good engineer, you know what happens if you get your engineering degree and then you still learn nothing, and then you work sales. That's how it goes. If you know stuff, then you get to be an actual engineer. So this is what the knowledge actually is. Set up the integral from the shape that you hold in your hand, and then let the computer integrate that. So what I have is right-hand side only, because my dx, why is the dx the one that I'm looking at? Because that's the end one. It's always the end one is the boss. The height of it is y, which is the inner one. But the outside one is the dx, so that's the one that I'm looking for. Now, this one tells me that the dx is moving from left, 0, to right, 4. And that's why we have half of the circle. If I want a full circle, -4 to 4. Can I modify this to just take a quarter of a circle? Sure. If I want just the upper quarter of a circle here, it's still 0 to 4, but this becomes 0, right? Because the dx would have to go from 0 to square root positive. You can isolate any quarter you want. You can't do the eighths and those half slices and the other stuff that they do in pizza. We will do that in the next lecture when we do this in polar coordinates, right? Then you will be able to chop it up in any way you want. Right now, we are very limited. Why I don't want to solve this problem? Because when I get to integrate these puppies, I have to use trig sum. Well, screw that. Because the next lecture, this transforms into equation -4 and +4. So, hey, right? It's going to be cool. So we're not going to do it now, because tomorrow we get to make a joke out of this problem. But this problem has a huge value right now for you to chase the 4 limits and to chase the things on how they translate to the circle. What is one of my favorite questions for the exam? Getting it right. Give you the circle, and I say, give me the limits. Just set up. I don't care about you calculating stuff. Just set up the third quadrant. That's it. Set up the third quadrant. So let's pretend that's your exam question right now. You have this, but I don't care about that. Just give me the third quadrant. What is the third quadrant? This is the third quadrant, right? 1, 2, 3. Give me the limits. So put the 2 squiggly integrals, and give me the limits for the third quadrant. That is your exam question. And it's okay to talk to people around you and check your answers or brainstorm and completely interrupt them in doing unrelated stuff.
it out loud.
Guess not.
Is this our break? We're just playing games. He asked a question.
He asked a question.
You are so disconnected. I just asked an exam question. Everyone is thinking, you just woke up. It's like, is it a break? It's like when I drive my kid somewhere and he's passed out and like, are we there yet? Yes. So now that you asked me if I'm playing, I'm kind of. I want to install the what's the candy thing. What's it called?
Candy Crush.
Thank you. Yeah, I'm gonna look it up now. Install it just because you asked. So every next time it's like, oh yes, look. I am. I got 2 Twizzlers in a row. Is that Twizzlers? It's candies. I don't know. Anyway, so the question is, I said here in blue, limits for third quadrant. Squiggly integral. We're going to have f of xy, and we're going to have dy dx. So what are my x limits? -4 and 0. Perfect. I love it. -4 and 0 because my dx that it's going to ride in here, right? It's going to start at -4 and complete its journey at 0 as it goes from left to right. So -4 to 0. Perfect. How about the inner ones? What do I have on top? 0. Because the top is the x-axis, that's y equals 0. These are the y limits now, because they correspond to the inner dy. So y equals 0 is on top, which is x-axis. And what's on the bottom? The orange negative square root. Yes, perfect. So these limits over here will bound just the third quadrant. So I can chop this in any of the halves, in any of the quarters, and so on. Or you can have the full circle, -4 to 4, negative square root to positive square root. That would be the full circle. Now, we do not want to calculate any of this here because it's annoying. You have to use trig sub to solve these integrals. What we want to actually do is transform this into the polar coordinates and make a joke out of this problem. But that's next lecture. So let's focus more on task at hand, which is more 16.2. They want you to set up, so problem 41, guys, let's go. Set up limits for dy dx, where R is the triangle with vertices 0, 0, 2, 0, and 1, 1. So they're not asking you to integrate, they're not giving you f of x, y, they're just asking you to set up the limits, and they give you the dy dx, and give you the 3 vertices for this problem. So let's go. What is the absolute must? Step 1. What's something that you absolutely have to do? Yes?
You're integrating x from 0 to 2.
That's not the first step.
Draw it.
You draw it. that has to be without thinking. The first step, you have to see.
I talked about the sideways one, right? So you look at the
It's still
sideways
doing it in
one.
your head.
It's in
Well, no,
his
it
head.
seems like he's like,
But
It's in his head.
It
It's
can-
subconscious. You
can
can't
you
figure
bring
out
so
what
many-
it is.
I'm looking at this now.
Because then I'm like,
LNGIT, and then I worked two years with Calculus, and then so it goes 12 years. Stuff that I say the students come up with, but they don't draw.
they weren't doing it in their heads correctly.
Yes.
That's the problem.
How many boxers do you see walking into the second round of the fight like this?
Right away.
So,
Get the metaphor, but oh, okay.
you're asking to actually get, yeah, you're asking to,
Oh,
yeah, to something that looks
what
simple
unit does
to get, to get knocked out. Because that's usually when you knock out, right? It's so complicated.
examples only on top
That
of
you
each
can
other?
have.
Versus 13 and 14.
sorry.
No, no,
Third one is
17. 17, he said, is no.
No, he said that.
So,
2 or 3 sections of 17 will be learned post third exam, and they will be on the final. That's what it was. If we can get to it.
so just work 1 year each, just like that, and then next year we'll go. I walked in. I was invited to a prom. I was invited to everyone, and I called everyone, right? I killed it the whole thing. I was a student, currently teaching, like you can't have that, right? You can't have that. Yeah. Didn't get it. Because there was extra some law. It was asking me education.
Yeah, saying
That's that position, right? 2 years later, 1 day,
So you want to win it?
rules.
but that
Okay.
was
I'm not a big hockey guy. I just want the St. Louis Blues to win because there was like a snap story. This girl with like this type of cancer.
That's what I do.
I think that team was the St. Louis.
And I got burned every time.
And the first time that she was like one of her.
All right, let's take a look at this problem together and set it up.
She went
So
aside from home.
we start from
So
our drawing.
I'm like hockey.
I have a point at 0, 0. I have a point at 2, 0. And I have a point at 1, 1. Oh, this is going to be nice and tricky and evil.
They make it insane.
I already love it.
Kevin Durant getting hurt.
Guys, this is evil.
That was the stupidest thing.
Look at this. If you want a dy dx integral, do you see the dy dx? This is a dx. What is going to happen as this dx starts going across? What happens with the top? Is it writing the same function? No. If you are forcing dx integral here, you have to have 2 integrals. One for the left side and one for the right side. If you are forcing dx dy, you will only have 1 integral. Yes?
Couldn't you do it with one function? Just the absolute value?
Yeah, but you still have to integrate in 2. So sure, you can combine it in the absolute. Yes. But when you start computing it, you still have to break it
You gotta
apart.
separate it.
Yes. So sure.
So,
So let's let's go. The first order of business is to draw. Second order of business is what are my functions? What's my, let's say, let's call this g, and let's call this h. Now these are linear functions from like negative fourth grade. So g is definitely just x, right? Because it goes from 0, 0 to 1, 1. So that's just x. And function h is going to be, as you can see, it's going to hit through 2, and it's negative 1 on the slope, so it's negative x plus 2. Now, you can actually use the 2 points and do the slope with the y2 minus y1 and go to the whole spiel to figure out these two functions. So now I have my two functions. I have that the g of x, which is actually a y, in this case is x, and I have that h of x is negative x plus 2. So now that I'm setting up a double integral of whatever the function goes in here, and it's going to be dy dx, I go from 0 to 1 on x, because I can only go, g is only one function, right? And then I go 0 to g, which is 0 to x. Plus another double integral, and this one goes from 1 to 2 for the other half, and I go from 0 to negative x plus 2, f dy dx. So these two integrals together, right, one covers, so this shade over here is the first integral, and the I don't know, here is the second integral, right? But can I do this in one shot? Yes! If I use dx dy. So this is dx being a boss. If dy is the boss, then my triangle is dy like this. And that's going to have a single integral, but now my limits are y on the outside, so that's going to be from level 0 to level 1. And then I have to flip these functions, because this is y equals x, now I need x equals y. And this is y equals negative x plus 2. I need to solve this for x, so x equals 2 minus y. So this one is 2 minus y that goes on top, and the one on the left is just y. So now when I integrate, I will get integral in respect to y, and then I integrate in respect to y, and using numbers to get a number. So you can see now that if I use one way, I have to use two integrals, but if I use the other way, dx dy, I get to use one integral only. Now that's something that you have to practice. And guys, what you just witnessed here is the way to change order of variables in integration. You have an integral, you draw the region, you have all the functions in that region, you flip all the functions, and then you write the integral in the opposite order. So changing the order of integration for 16.2 is not trivial as 16.1. 16.1 is the cheap one. You can stack them in any order you want. Just make sure you bring their limits with them. So that's pretty much it for... there is one more concept, but we can deal with that tomorrow. Let's take a break, and after the break, we're going to take a look at the review, if you have any questions, and talk about the exam. So see you in about, I don't know, let's say 420 seconds.